Hi all, we're finally going to ask a question that we've been avoiding about Taylor polynomials for quite some time, and that is, so Taylor polynomials are supposed to approximate the function that you start with, but how far off is your approximation exactly? So we're going to look at, given some x value, how far is the nth Taylor polynomial at that x value away from the actual value of the function. Now, our hope here, secretly in the background, is that if we measure the distance between the two just by subtracting, so take this difference, and then take an absolute value because we actually don't care which is bigger, we just care about the distance between them. Our hope is that as n gets bigger, so as n goes to infinity, our hope is that this difference is going to go to 0. Because if that's the case, if that limit is 0, then the Taylor series is equal to the original function at that x value. Okay, but that's really just a hope. We have to actually do some work to see if this actually is true in general. It's actually not always true, but we'll need to measure how big this error, this difference between the Taylor polynomial and the original function, can possibly be. To do that, there are a few preliminaries to take care of. Just some facts to remind you about or to explain. So first thing is that if you have any function, it's not f in this case, so let me call it g. If you look at g of b minus g of a, that is the integral from a to b of the derivative of g dx. This is just the fundamental theorem of calculus. Well, it's one form of the fundamental theorem of calculus, and it's a form that we're going to use at a critical point in what is to come. The second thing is that if you have any function and you integrate from between two values, g of x dx, if you take the absolute value of the integral, that is going to be less than or equal to the integral from a to b of the absolute value of the original function g. Now, this probably isn't something you've seen before, but there's a good reason that this is true. On the left-hand side of this inequality, this is the net area from, under the graph of g of x, from a to b, or the signed area is another way of expressing this. In other words, since g of x might sometimes be above the x-axis and sometimes below, this integral, the positive and negative areas will cancel. But if you look at the integral on the right-hand side of the inequality, this integral over here, this isn't the net area. Because of the absolute value inside, all area in this integral counts as positive. So this is the total area under the graph of g of x from a to b. So in the integral on the right, no area cancels. In the integral on the left, some area might cancel. And so that means the total area is bigger than the net area. Because in the one on the right, no area has canceled. It all counts as positive. So that just accumulates more area. All right, and then the final fact that we're going to need is that if you take the nth Taylor polynomial for x and you take its derivative with respect to x, what you get is the n minus first Taylor polynomial for, I'm sorry, I'm missing an f of x up here. If you take the nth Taylor polynomial for f of x, and you take its derivative, what you get is the n minus first Taylor polynomial for f prime of x. This takes a little bit of calculation, but if you just take the nth Taylor polynomial for f of x, that's the sum from k equals 0 to infinity, to n of kth derivative at the base point divided by k factorial times x minus a to the k, and then take a derivative. What you get is the sum from k equals, you'd like to start at 0, but remember the k equals 0 term is a constant, and the derivative gets rid of that constant, up to n of f of k, kth derivative of f at the base point, over, now when you take a derivative, this k in the exponent, it comes down because of the power rule, so you get k minus 1 factorial times x minus a to the k minus 1. And then if you notice, our powers are now off. We have a k here, and a k minus 1 in our exponent, and a k minus 1 in that factorial in that denominator. So if we, to make things line up the way we're used to, let's let j be k minus 1. So we're just relabeling the terms in our sum here. So j, if k starts at 1, j is going to start at 0 because j is k minus 1. And if k goes up to n, then j is going to go up to n minus 1. And so we get a derivative of f here, but k is j plus 1, so we get a j plus 1 right here at a over k minus 1 factorial, that's j factorial, times x minus a to the k minus 1, and that's j. Okay, and if you look right here, this j plus first derivative of f, this is the jth derivative of f prime. All right, so finally we find that if you start with the nth Taylor polynomial of f, you take a derivative, you get the n minus first Taylor polynomial of f prime, which is what we have right here. Okay, with all of those preliminaries out of the way, finally we can attack the problem of how big is the error between the nth Taylor polynomial and f of x, which we will do in the next video.